Okay, so welcome back. So it's a pleasure to introduce the last speaker of our Monday morning session. Will be Sergio Morales Tejera from IFT Madrid, and he will tell us about out of equilibrium anomalous transport in holography. Please, Sergio.
Okay, so thank you very much. So as you said, I'm going to talk about anomaly induced transport in holography. Is this not working for some reason? Sorry, I don't know what's happening.
Are you in full screen? Yeah, okay, now it works.
Yeah, I don't know what happened. Anyway, so I will first start talking about the physical problem we're interested in. I will spend most of the time in that part, which has to do essentially with the Chiral anomaly-induced transport in the Quark Gluon plasma. And then I will tell you how to model this chiral transport in holography and show you some results we have obtained so far. Okay, so let's begin by a very quick review on anomalies. So we know already that symmetries are very important in physics. You have some transformation that leaves the Lagrangian invariant, and then you get, by Noether's theorem, a conserved current. So far, everything is classical. Now, if you try to quantize the theory, it may happen that this symmetry is broken by quantum effects. And what do we mean by that? Well, if in your classical theory, your Lagrangian was invariant, now in your full quantum theory, you have to use a more complicated object to describe the dynamics, which is this path integral. And now this part here, which are the measure, is not invariant. This is what we mean by the symmetry being anomalous or broken by quantum effects. Now, how does this manifest at the level of the conserved nether current? The thing is that now it will no longer be conserved. Okay, this is very elementary. And now let's move to a specific example, which is that of the chiral transformation or the chiral symmetry. It is interesting for us because in the Quark Gluon plasma, the chiral symmetry of QCD is restored. And so the quarks all around are chiral particles. And hence we will have this symmetry we have to study, okay? So essentially we rotate left-handed and right-handed fermions independently. We observe that this is a symmetry of the Lagrangian, and we can define two conserved currents. If you want to call it left-handed and right-handed currents, or it is more useful for experiment and more customary to use the vector and axial currents, which I define down here, okay? And now the question is if this symmetry is anomalous or not. Well, the thing is that it depends, and it depends on the matter content of your theory. In particular, you will find this coefficient, which is called the anomaly coefficient, which is some sum of the charges of left-handed and right-handed fermions in this case. And if this coefficient vanishes, then the symmetry is perfectly okay. It is not anomalous and everything works. But if this coefficient is different from zero, as it happens in QCD, then your symmetry is anomalous. Okay. Now, what is really curious and interesting from this is that even though it seems like a mathematical subtlety that you get this non-conservation of the current or of the measure, and even though it is an intrinsically microscopic phenomenon, it can give rise to some collective macroscopic phenomena. And these are what we call the anomaly-induced transport. In this context, we call it chiral anomaly-induced transport because they come from the chiral anomaly in particular. So I will be mainly concerned with two of them, which are the chiral magnetic effect and chiral vortical effects. I will now explain what they are. So first, let's begin with the chiral magnetic effect. For that, we can think of the Ohm's law that we know from kindergarten, where you have some material, you apply an electric field, and you get an electric current. Okay, this is very, very basic. Now you can ask the same question if you had a magnetic field. Now I have a material, I apply a magnetic field, and I want to know if I will get some current or not. If I get a current, then this is the chiral magnetic effect. And you may wonder why this is something very new if it looks so trivial or so essential. And the thing is that And the transport coefficient of this effect has to have some special symmetry properties. For example, it has to be even under time reversal, it has to be odd under parity. And this is usually classically forbidden in our materials. And now the thing is, if you have chiral particles in your system, you can have chiral chemical and axial chemical potential, and this satisfy the properties we want. So this can be viewed as our transport coefficient here, okay? And let's explain how it happens intuitively, okay? So we have a material with chiral particles, like left-handed and right-handed. We apply a magnetic field, and because of the interaction of the magnetic fields and the particles, the spin will tend to align. And because chiral particles have the spin correlated with the momentum, you will get a collective motion, okay? So right-handed particles will move in one direction and left-handed particles in the other one, overall, okay? Now, if you have the same number of left-handed particles than right-handed particles, of course, you will not see any current. You won't observe anything because they will cancel out. So this is why you also need this chiral imbalance. You need a chiral chemical potential that is different from zero. And we obtain the chiral magnetic effect, okay? This is the physics. Now this effect can be computed from in several ways. For example, you can use Landau level physics, and you get this form. And surprisingly, what you observe is that the current is proportional to the anomaly coefficient. So if the symmetry is anomalous, you can get a current, and if not, there is no way you get a current. This is why we call it anomaly-induced transport. Now this current is very special, among other things, because it is non-dissipative. This can be understood in several ways. One can argue that the current is topologically protected, and then hence it cannot dissipate. Or one can argue that under time reversal, the current is odd under time reversal, so is the magnetic field. So this thing has to be even under time reversal, and hence it cannot generate entropy, and it won't dissipate. This chiral magnetic effect has first been measured already in some materials, which are the Dirac materials, semi-Dirac metals, for instance. This was the first one, zirconium tellurium 2, and now it has been already measured in some other materials. The Chiral Vortical effect is very similar, only that now instead of applying a magnetic field, what you are having is some general rotation of the system. Now, of course, this is not really consistent with relativity, because at some point, if you move in the axis, you will get some velocity which exceeds the speed of light. But you can always consider a small enough cylinder and define your vorticity, and you can get this effect. This is the form it takes. Now it's proportional to the chiral anomaly coefficient that we saw before. And this other one, which is related to another anomaly, which is mixed gauge gravitational anomaly. For this effect, we can have a similar intuitive picture. And now, for some reason, you also need to have a vector chemical potential, which is different from zero, okay? I will talk mainly about the chiral magnetic effect, even though we have studied both, and I will make some comments on this. Now, why is this interesting? Well, as I anticipated before, because of the Quark Gluon plasma. And the Quark Gluon plasma, as we know, is a new state of matter that happens. Okay, here we have a cartoon of the phase diagram of QCD. It happens at high temperatures with some baryon chemical potential. It is expected to have been a phase of the early universe. So if we understand what happens in the Quark Gluon plasma, we can maybe make some prediction on what happened at the early universe and the signatures it may have led so far. And it's also been reproduced at the particle accelerators as LHC and RHIC. So you take the nuclei, you accelerate it, you make them collide. And at the very early stages also of this collision, you will form a quark gluon plasma, which is very short-lived. It would live in a very strong magnetic field, etc., etc. Now, there is some tension because the chiral magnetic effect is being, at the moment, looked for at LHC and RHIC, okay? And they have already shown some results, and there is a bit of tension between both. I mean, not like the Hubble tension, but a bit tension. Because in LHC that works at higher energies, you would naively expect that you have a higher signal from the chiral magnetic effect. Whereas at RHIC with lower energy, lower magnetic field, you will get a signal that it should be smaller. And what they claim is at RHIC, they have something that is consistent with the chiral magnetic effect, but at LHC, the results are also consistent with zero. We should understand what is happening here. There are some ongoing experimental improvements going on. They are about to publish the isobar runs results. Well, they have been about to publish them for some months already. They should come soon, I hope. But if the tension remains, then we have to resort to the theory and see try to find some reason maybe why this could be the case. Okay, and now you may wonder, why do we expect the chiral magnetic effect to be present in the quark gluon plasma? Well, as I said, in the quark gluon plasma, the chiral symmetry of the standard model of QCD is restored. So first we have this, and the other two ingredients we have are magnetic field and chiral imbalance. The magnetic field is easy to understand, so you have charged particles moving at very high velocity, so you will get a magnetic field for sure. For the chiral imbalance, it's a bit more intricate because initially you have chiral balance. You have the same number of right-handed and left-handed particles. The thing is that because the SU3 group of QCD is non-compact, you can have topological non-trivial solutions which are also chiral and can transfer chirality to the quarks via the chiral anomaly precisely. This is the mechanism proposed. I don't know if it has been checked somehow so far, but this is the reasons why we expect the chiral magnetic effect to be present here, okay? Now the quark gluon plasma is a very complicated system to study in physics. First of all, because it has been observed that it's strongly coupled, so perturbative QCD will fail. Lattice methods also fail because, well, on the one hand, because if you want to study the real-time evolution of the current, you will have to deal with this sign problem that they have in lattice. And on the other hand, because this is a macroscopic phenomena, and if you want to really study it, you have to include a high number of particles, and you will very quickly exceed the computational capacity of your computer. And finally, there are some non-equilibrium quantum theory formalisms that may give us some faithful answers, but they are in general very complicated. So holography seems to be the best alternative to study this.
Hey,
so
sorry,
now I will focus on...
Very naive question.
Yes, go on.
So how strongly coupled is supposed to be the QGP? Because, I mean, the diagram just showed, wasn't the idea that if you go to LHC, you go to very high energies and then QCD should be asymptotically free and everything?
Yeah, I think one of the reasons they say it's strongly coupled is because they have measured the shear viscosity and they find it to be in agreement with the prediction of holography. Okay. And this is the reason that I have heard so far.
Yeah, I heard that, but so this is the only one, basically.
Yeah, maybe yes. I don't know. I don't have more insight in that. Maybe somebody in the audience can contribute.
Okay, thanks. Sorry for that.
Nothing. So now let's see how we can model the chiral transport in holography. For that, we will use a bottom-up approach. So we are going to cook up the model. We're going to build it so as it reproduces the phenomena we want. So first of all, of course, we have Einstein gravity with the anti-de Sitter solution, and nothing new. Now we want to have two currents, the vector and axial currents. And in holography, these are dual, of course, to the gauge fields in the back. So we introduce two gauge fields, vector and axial. Usually the models you see for chiral transport, and they only have one of the gauge fields. And this is motivated because then this can be directly related to some truncation of supergravities, etc., related to string theory. But here we want to do it bottom up. We want to somehow compare with experiments, and we do it this way. Now, of course, here the chiral symmetry will not be anomalous yet. We have to introduce something to make the symmetry in the dual quantum field theory anomalous. And these are the Chen-Simon terms, one for the axial part, one for the vector part. Essentially, these terms are gauge invariant up to a boundary term. So this boundary term is the one that reproduces for you the chiral anomaly. This is known already for 20 years. This is nothing new. Also, and this is more in view of modeling the chiral effect, because as I said, there was a coefficient proportional to the mixed gauge gravitational anomaly. And this is the one that implements the gauge gravitational anomaly. Okay, so far so good. Up to here we will have anything. Also, in view of a more sort of realistic scenario in condensed matter physics, one should include impurities and dissipation of momentum. There are several ways to do it. We do it explicitly and by the simplest way, which is including 3 scalar fields with a very simple profile that I have written down here. So if you plug this in the equations of motion, your equations of motion will still be translational invariant because everything enters through derivative, but you will still get dissipation. So this is a very simple way. You can view, if you want, K as some sort of homogeneous distribution in the dual quantum field theory. Now you put the boundary terms needed for making the variational problem well defined. There should also be some contribution stemming from this term, but we have seen that it doesn't affect what we're studying, so we don't include it. And finally, this SNF, null fluid, we call it, and this has to do what we are doing with the model, okay? What we're doing is we find the equations of motion from this action, and we find the equilibrium solution. After that, we drive the system out of equilibrium. So we perform a quench, and we see how it relaxes back to equilibrium. And how do we drive the system out of equilibrium? Well, with some external source, which is thought to be encoded in this S-null fluid. Okay, so now let's go already to the answers and the solutions and everything. So for the chiral magnetic effect, we have some, okay, something I have not said. In the first study that actually is not mine, it's from Carl Landsteiner, my supervisor, and his previous student, Pendas. And they were studying the chiral magnetic effect at a small magnetic field, so perturbatively in the magnetic field. This is, of course, not a very good model because, as I just said, in the LHC and RHIC, you expect to have very intense magnetic fields. But okay, at the time, this was a preliminary study to see what it happens. Actually, at the moment, we are studying the case of arbitrarily intense magnetic field. There is also a related talk on this regard. The last talk of this evening is about this. So if you're interested, you can go there and check something. But okay, at the moment, let's just discuss the perturbative magnetic field case. Also, we studied the perturbative chiral vortical effect. Now, this is more meaningful to do it perturbatively in the angular velocity because, as I said, you cannot have large angular velocity without violating relativity, so you restrict to a small neighborhood of your rotational axis, and there your angular velocity is expected to be small. So anyway, for the perturbative magnetic field, we have this ansatz, which is anti-de Sitter. This is the background solution. We can find F analytically and everything in this Vairia metric. And then we have to include the perturbations, here the magnetic fields, this will give us the currents, etc. Okay. Also from the holographic dictionary, we compute the chemical potentials, the temperature and everything we need. And we solve the system numerically and we see how the current responds. So, okay, using this is simply the variation of the on-shell action with respect to the corresponding fields. Okay, this will give us vector current, this will give us axion current, and this will give us the energy current. This is the time seed component if we apply the magnetic field in the seed direction. And these are just this B2, H2, and H4 are the subleading coefficients of these fields V, A, and H. Okay. So let's see the solutions. This is for everything I will show now is for the Chiral magnetic effect. This is the vector current, and we study the dependence with how abruptly we drive the system out of equilibrium. Okay, we can do it smoothly, we can do it abruptly. Larger taus means that we're doing it smoothly. This is the green curve here. Of course, if we do it smoothly, we would expect the system to have sort of more time to thermalize, and it will go closer and closer to the equilibrium solution that we show here in the dashed line. Whereas if we change the system abruptly, we see more deviation. Now, what is interesting here for us, for what we want to study, is that there is some sort of delay. You can see that the current takes some time to build up. So we change the system, the dashed line, we can see here that we are driving the system out of equilibrium, and the current stays constant a bit more time, and after that it starts to relax. And why is this delay interesting in view of the Quark Gluon plasma? Well, precisely because the magnetic field in the particle accelerators have a short lifetime, okay? And this lifetime of the magnetic fields is inversely proportional to the energy at which we are. So for instance, as at LHC, we are working at higher energies, and so our magnetic field will be very short-lived, whereas at RHIC, we work at slightly slower energies, so the magnetic field will live a bit longer. Now the thing is that if your phenomenon, if your current takes some time to build up, it may be the case that you switch on the magnetic field and you switch it off before it starts to produce any current. And this might give some intuition or might explain why at LHC they see a smaller signal. Is this clear? Okay. So this is the main thing we study at the end, the time delay and its dependence with everything. We can also study how it varies with the moment of relaxation parameters. So k equals 0 is no impurities. K equals 2.6 is a lot of impurities. We simply studied, we observed just sort of a transition between two regimes, one where it bounces a bit the current and the other one where it decreases monotonically. And this simply can be understood in terms of the quasi-normal modes of the system. So here I show the real part, and here I show the imaginary part. And there are, of course, several branches, but if we only keep track of the longest lived, we observe that the system relaxes with a real part up to some value of k. So this would give sort of oscillatory behavior. And after that, the other branch dominates, and this one has 0 real part. So this is why we observe here a bounce, and here we observe monotonous decrease, okay? We can do the same for the energy current. Of course, if we have no moment of relaxation, the response in the current is trivial because momentum is conserved. And as soon as you start putting impurities in your system, you will see how it relaxes to some other equilibrium value. And again, you can also here you can see there is some delay in the response. Also here in the axial current, you observe there is a delay in the response. Here the final state without momentum relaxation is a bit lifted with respect to the final equilibrium state with moment of relaxation. And this has to do with some contribution that arises, which does not dissipate, cannot dissipate if momentum is conserved. So the dashed line is the pure anomalous equilibrium, and the black line is that one plus some contribution that doesn't dissipate. That can be understood in hydrodynamics, okay? And here are also the quasi-normal modes for these fields, which are coupled. And we see that there is a minimum, and this explains why the energy current sort of finds a threshold here for k equals 2.4, and it relaxes later for higher or lower values of k, okay? So here I show the delay I was talking about. We can do the simulations and simply define according to some arbitrary criteria what we call the delay. And we can study it numerically. And we have also proposed to study, okay, so here is with the quench parameter, with how abruptly we change with equilibrium. Here is with momentum relaxation. And we have proposed a very simple, intuitive way of computing it analytically without having to solve all the equations of motion. We find a remarkable agreement indeed. And as I said, this might be at the core of the disagreement between LHC and RHIC. So now the conclusions. Okay, so we have seen that the Chiral anomaly induces for us novel macroscopic non-dissipative transport phenomena. That some of them, for example, the Chiral magnetic effect, are at current search at LHC and RHIC, even though there is some tension, and for that tension we have proposed this model. Even though we want to do a more realistic model, because again, this was done for perturbative magnetic field, and now we are doing it for arbitrary magnetic field with more physical considerations. So we really want to do something that an experimentalist could use somehow. And also we have seen that holography seems to be well suited to deal with the Quark Gluon plasma. And of course we can generalize, we can make the charge of the system time dependent, the chemical potential, because as I said, we start with a zero axial chemical potential, and after that, after some time, you would expect to have something that is non-trivial. You can also include time dependent magnetic field, even though this is very painful and we don't go there so far. These are some references I have used. This is the paper of Karl Steiner and his previous student, and this is the one we have released in June. So nothing else. Thank you very much.
Thank you so much, Sergio, for the nice talk. So questions from the audience. No questions?
I have one question, not directly related to what you shown, but tangentially. So recently in condensed matter theory, another chiral anomaly has been found, the one related to torsional defects in the lattice. So I wanted to ask you if you have any idea if torsional anomalies could be important in describing the transport properties of the Quark Gluon plasma, or they won't play any role whatsoever.
Okay, can you talk a bit more about these torsion anomalies? Like, where do they go up, or?
Yeah, so they are basically like gravitational anomalies. They have a t-square scaling, and instead of the curvature tensor, you have the torsion tensor that couples to the whole thing.
Okay, but then the torsion, this is the torsion in the holographic, in the bulk part, right? Or are we talking simply about the material?
The material.
Okay, so it might be relevant. I would expect it to be more relevant in the Chiral Vortical effect, where we have already seen that it has some contribution from the gravitational anomaly, but it should be I mean, it can be studied. I think my supervisor at some point was thinking about how to implement this in holography also.
Okay, good. Thanks.
Thanks to you.
Anything else? Other questions? Nothing? I guess you're all hungry. Okay, good. Then let's thank Sergio again. And we will meet again this afternoon at 5:15 for our afternoon session. So I hope to see you all there. Thanks a lot.
Okay, bye.